Hi everyone, my name is Mohammad Adil Inam, and today I'm excited to present our work on forensic analysis of configuration-based attacks. This is a joint work with University of Virginia, UPM, and LUMS. So audit logs maintain a history of events that occur during system execution. Audit logs are an invaluable forensic tool for threat investigation since they record the interactions between different subjects and objects within the operating system. To simplify investigation, these audit logs can be parsed into provenance graphs, and upon an indicator of compromise, these provenance graphs can then be queried by analysts to identify the root cause of an attack. While audit logs are an invaluable tool for forensic investigations, for certain attack classes, they may not contain enough information for complete attack reconstruction. So a question that comes up here is that what happens when key attack behaviors can't be explained accurately through audit logs? To explore this question, let us consider the case of configuration-based attacks. Configuration-based attacks are attacks resulting from improperly configured software. Our studies on CVEs reported in the past decade revealed that configuration-based vulnerabilities on average constitute about 4% of total reports, and we have seen a rising trend in the recent years. In addition to their prevalence, these attacks can also have dire consequences. OWASP ranked security misconfigurations as one of the primary reasons for data breaches. For example, in July 2019, a configuration-based vulnerability in Capital One's firewall leaked the credit card information of more than 100 million customers, and there are many more examples like that. Given the prevalence and security implications of configuration-based attacks, it is important to analyze whether these attacks can be effectively investigated using existing audit infrastructures. To explore this, let us go through a case study in which the attacker exploits the configuration of different systems. We consider a simple scenario in which a company uses Exponent CMS, a web content management system, to manage its website. Moreover, the CMS is connected to a Redis database at the backend. For Exponent CMS, the configuration state is stored on disk, whereas for Redis, the configuration state is maintained both in disk and in memory. The attacker in this scenario performs a series of attacks. First, the attacker exploits an underlying vulnerability in Exponent CMS and injects code into the configuration file of the CMS. In this attack, the configuration state of Exponent CMS is updated on disk. The attacker then executes arbitrary system commands and exploits an other vulnerability in Redis to dynamically update its configuration within memory and eventually gain privilege escalation. In this attack, the in-memory configuration state of Redis is updated. After realizing the database compromise, an analyst begins investigation using a system-level audit logs, which are collected at a system call granularity. The analyst discovers the shell that resulted from the code injection. He then issues back and forward trace queries on the provenance graph to identify the root cause of the attack. The identification of root cause is important to expose any underlying system vulnerabilities and to also prevent similar attacks from happening in the future. However, root cause identification presents various challenges in this case due to the lack of semantic insight in system logs. First, the whole system provenance logs do not specify the configuration fields that were modified in the file-based attacks. As a result, the analyst is unable to distinguish between authorized configuration file writes and unauthorized code injection file write. Moreover, to make matters worse, in a memory-based attack on Redis, no events in the log describe the malicious in-memory configuration change, which widens the semantic gap even further. In short, the system-level logs paint an incomplete picture of the attack. To proceed with the investigation, the analyst then turns to application event logs, which contain info, debug messages, etc., in hopes to find some additional information on the attacks. However, neither Exponent CMS nor Redis creates any record of file-based or memory-based configuration changes. Therefore, the application logs in this case provide no additional insight. To further validate this observation, we surveyed 18 widely used and prevalent applications along with all the applications used in our work and found that none of them create records of file-based or memory-based configuration change events, rendering application logs ineffective for investigating configuration-based attacks. Keeping the challenges associated with investigating such attacks in mind, we set out to design a system with the following design goals. First, our provenance tracker should have support for fine-grained detection of application state changes, such as configuration changes, regardless of the update mechanism, be it file-based or memory-based. Second, our provenance tracker should correctly associate application state changes to external system events collected by whole system trackers. For example, we should be able to attribute the change of a configuration to a specific process or a specific user. Lastly, our provenance tracker should be able to efficiently audit application state while avoiding high runtime or storage overheads. To achieve these goals, we present Dossier, a specialized provenance tracker that audits application state changes in a target application and encodes the necessary information into OS-level audit logs. Dossier supports the main interface of configuration changes, that is, changing application state-related program variables in memory, typically through a user admin interface, as well as changing application state files on disk. And while we do motivate our approach through configuration-based attacks, we note that Dossier is a generic tool for auditing any application state information maintained in program variables. So Dossier consists of two main components. For memory-based tracking, Dossier's workflow is as follows. The system administrator first annotates configuration variables to be tracked in the target application after analyzing the source codes. Dossier uses these annotations and performs LLVM-based novel static analysis to determine all the sites within the program where the annotated variables are updated. Dossier can be configured to propagate both explicit as well as address-dependent implicit flows as shown in line 8 and line 11 respectively. Dossier then applies multiple filtering techniques to rule out any false positive if necessary. This can include logging one update for a basic block or logging updates within specific functions, etc. Finally, Dossier instruments part of the application to track changes to the annotated variables. And these instrumented target applications are then capable of emitting configuration change log events. For file-based tracking, Dossier takes as input a list of sensitive configuration files to monitor for content changes. It then loads a custom kernel module that intercepts a specific set of system calls such as write, pwrite, writev, etc. If the given system call modifies a sensitive configuration file, Dossier extracts and logs the data buffer for that system call along with other metadata information such as PID, TID, etc. Finally, the system call is returned back to the system call handler. During our experiments, we found out that some applications update the entire configuration file even if they're changing a small part of the file. For example, in the case of Exponent CMS, when the port is changed from 25 to 1505, the configuration file is rewritten through 6 system calls of 1 KB chunks, with the port getting updated in the 4th chunk. This results in 2 bytes getting cascaded to the 5th and 6th chunks respectively, as can be seen in the figure. We observe 2 things in this example. First, we cannot compute the correct file delta by comparing the buffer of 2 write system calls writing on the same file offsets. For example, if we compare 1E with 2E, because they write to the same file offsets, we will reach the incorrect conclusion that 2 bytes were added to the front and 2 bytes were removed from the end in chunk 2E. In reality, neither of the conclusion is true. Similarly, we can also not compute the correct file delta by comparing the complete file state every time there is a write to a disk. Returning to the update, if we compute the file delta between 2D and 2E system calls, we will again reach the incorrect conclusion that 2 new bytes were added and 2 new bytes were removed from chunk 2E of the file. And both of these problems arise due to the ripple effect which takes place when the complete file is rewritten. From the example above, we can see that we only need to compare the first and the last state of the configuration complete file during an update to compute the correct file delta. Based on this observation, we developed an algorithm that clusters system calls together to compute accurate file deltas and remove any unnecessary logs. The details of our algorithm can be found in the paper. At runtime, in addition to collecting whole system provenance logs, Dossier collects the memory-based configuration logs from the instrumented applications, as well as the file-based configuration logs emitted by our kernel module. Finally, during the investigation phase, upon an indicator of compromise, Dossier combines the configuration logs with the underlying system logs to create holistic provenance graphs that link configuration events to system events in a causally correct manner, facilitating precise investigation of configuration-based attacks. Now, going back to our case study, we now consider the case when Dossier is running on the compromised system. The holistic provenance graph generated by Dossier solves the challenges associated with prior techniques. It contains the information about the file-based as well as the memory-based configuration changes that happened during the attack. Therefore, an analyst in this case is able to precisely investigate the root cause of the attack that led to code injection and that led to privilege escalation. To evaluate our system, we evaluated the file tracking and memory tracking components of Dossier, both in terms of the runtime overhead and correctness. To evaluate the file tracking overhead, we measured the time overhead associated with write-based system calls with and without using our kernel module. Our results reveal that system call interception within our kernel module leads to an average overhead of about 3%. Similarly, the overhead associated with logging configuration writes in our kernel module is about 4% on average. However, this overhead is inversely related to the percentage configuration writes. As the percentage configuration writes decrease, we see, as shown in the figure, that the overhead associated with our Linux kernel module is essentially reduced to the overhead of system call interception. Moreover, we also evaluated our file tracking module on various micro benchmarks such as lmbench, postmark, and blast, and observed a maximum noticeable overhead of only 5%. Dossier is able to achieve these low overhead numbers due to the kernel integration and by using built-in and efficient kernel logging functions. We also evaluated the overhead correctness of our application instrumentation using two popular open source applications that are Redis and Nginx Unit. To evaluate correctness, we provided Dossier different synthetic inputs and measured the correctness of our analysis against manually identified ground truth. Our results show that in most cases, the runtime overhead associated with application instrumentation is under 2% with a maximum observable overhead of around 8%. Moreover, we observed that when Dossier is configured to analyze implicit flows, the precision of our analysis is reduced. This is not a direct limitation of Dossier, but the inherent limitation of the underlying state-of-the-art static analysis tools. However, we do believe that system administrators have the option to disable implicit flows at the cost of completeness and still get reasonable recall values with very high precision. One might ask that would Dossier still be relevant if the developers were to log every configuration change event within application logs? In an ideal world, if that was the case, Dossier would not provide any additional utility. But unfortunately, based on logging practices, we have observed that developers typically do not prioritize security factors while making logging decisions. This observation was further validated in our study, in which none of the 18 prevalent applications we surveyed created any record for configuration change events, be it file-based or memory-based. Moreover, Dossier does suffer from a few limitations. First, since it builds on top of LLVM, due to open challenges associated with program analysis techniques, Dossier requires the application source code for static analysis as well as for instrumentation. Lastly, Dossier does require some manual annotation efforts on behalf of system administrators to specify configuration variables and files to be tracked. To conclude, we propose Dossier, a novel provenance tracker that logs changes to the application state. Our system features a lightweight kernel module for file-based tracking and uses program annotations and static analysis for memory-based tracking. Our evaluation on realistic workloads and attack scenarios shows that Dossier's generated provenance graphs can accurately reason about configuration-based attacks with minimal runtime overhead. Thank you so much for listening to my talk, and I'm open to any questions.